discussion of four-vector transformations and some important four vectors and relativity. And if I do what I intend to do, I will, at the end of the lecture today, actually connect via formalism the electric field to the magnetic field. So first, I want to talk about how vectors transform in relativity. And we want to create for ourselves several sets of four vectors that might relate energy and momentum, for example. We want relativistic quantities that will relate to the energy stored in the electric field, or rather in the fields. The fields themselves, and those might be vectors, and some of them will turn out to actually be tensors. So what I want to talk about first is how we want things to transform in special relativity. So we have a four vector that a space-time interval that we've already talked about, which was the ds squared. So this was a relativistically invariant quantity. There's c squared, the t squared minus dx squared. And that's a quantity that's invariant, we showed last time around, under relativistic transformation. Okay, we showed it for motion along the x-axis, but we set it up so that it has symmetry in the x, y, and z axes, so it should be the same. We also want to be able to define a point, some position in force space. And so I'm going to write the position force 4 vector as this. It's going to be x mu is ct, I'll write it in components, x, y, z. And we want the four vectors that we construct to transform in the same way as this position 4 vector. And we also want all the four vectors that we construct with the relationships between them to obey the rules of special relativity, which is that the physics is the same in all reference frames. That's probably the most important one. The speed of light is constant in all reference frames, right? So the first question is, how do the four vector position, how does that transform when we undergo, when it's observed in an inertial frame that's moving relative to the four vector that I just defined, right? And so what I could do is say, okay, what's the new four vector going to look like? So that's the transformed four vector. And let me choose a specific one. For motion along the x-axis, we know, but I haven't written down here, I'll write them down in a minute, the transformations between time and time prime, as measured in the transformed frame, in the moving frame, and x prime. So we know what the relationships have to be, but what I'm going to do is set up the relationship like this, that the position 4 vector in the primed frame is the sum over coordinates, and the formal way that we're going to number coordinates is that this is coordinate 1, 2, 3, so x1, x2, x3. The old position vector is dimensions 1, 2, 3, and this one is the 0th decision component. So we would write this as x0, x1, x2, x3, and hopefully by context, we'll figure out whether those are exponents or something that's denoting the dimension that we're actually working in. So you've got to, unfortunately, it's all in the context. All right, so this, in order to transform between the coordinates in one frame and the coordinates in another frame, and now I'm just moving along the x-axis with, let me choose a velocity, relative velocity. V. All right. Then these two sets of coordinates have to be related to one another. We already know the Lorentz transformations that relate them. And so I'm going to try to construct this in a more compact way. So I'm going to create a matrix here where these are the rows and these are the columns, if I remember correctly. Rows, columns? Somebody correct me.
Yeah, it's rows, columns. But
Rows,
how
columns.
you're supposed to tell from the... Because if you have mu on the bottom and then
It's
mu on the
first,
top,
second. It's really first, second.
but if you have my handwriting,
Not all of us have your handwriting.
Okay. So I want to find out what matrix takes me from this to that. And I know the Lorentz transformations already, yeah.
Should the exponent for the x be a nu?
This should be a nu, thank you. All right, of course, it doesn't matter which one's mu and which one's mu, but in order to come out with mu here, I'm going to have to basically sum over the common mu's over here, and then I end up with mu over on the left-hand side. Yes, thank you. And so I've just written it all out here, but actually this in the Einstein notation would look like this. A mu, mu, x, mu. Because you sum over repeated indices. Okay? So I need to find out what this is. And we already know the Lorentz transformations. So I actually know what that is. The tensor that makes the conversion is called the Lorentz tensor, Lorentz transformation tensor. And that A, mu, mu, looks like this. Gamma. I'm saving myself some writing here, and I'll define these in a minute. 0, 0. Oops. Oops. Please don't miss a line. The diagonal is gamma, gamma, 1, 1. And because this was a transformation along the x-axis, right? Remember, if you just think about the first term, I've got a transformation in time. C doesn't transform, but time does transform. And then, because I am moving along the x-axis, I have a transformation for the x component. And those are going to work together, all right? And the arithmetic that you would do here is just the straightforward matrix arithmetic. This quantity is also called a tensor. And I have to think about, I will probably later tell you whether it's covariant or covariant tensor. But it's a tensor, right? And what defines it to be a tensor, as opposed to just a matrix, is that we ask whether it transforms in certain ways. And later on, I'll define which ways tensors have to transform in order to be tensors. right? Covariant vectors are called that because they transform in a specific way from frame to frame, and contravariant because they transform in a different way from frame to frame, and tensors, covariant and contravariant tensors transform in different ways from one another. Yes?
Aren't they mixed because you've got one upper index and one lower index? Isn't this one mixed?
You don't have mixed. I don't know which this is. And I may have oversimplified last class when I said when it's upper it's this and when it's lower it's that. That's convention. And Ohanian doesn't obey all the conventions that I found elsewhere. So this thing, this matrix, when operating on the original vector, gives me the new coordinates as measured in the primed system. Okay, and so the position vector transforms in this way with that tensor transforming the two. Okay, so that's how the position vector transforms. We want all of the other vectors, the four vectors that we define, and some of them won't really, I mean, they'll look like a vector, but they won't appear to have the dimensions that you expect for a position vector. They won't, right? But all of the other four vectors that we define will, should transform in the same way. That is, when we measure a physical quantity in one frame, it should transform into the other frame using the Lorentz transformation matrix. Okay? I must have put that page back here. Yes, I did. All right. There's one other tensor that, well, there are going to be lots of tensors, but there's one other transformation tensor that's important to us, which is the one that takes the space-time vector, so CT, X, Y, Z, and turns it into the space-time interval. Okay? Got minus signs up there, so I need something that's going to produce minus signs. And so the other tensor of importance is G. I'm trying to remember where to put the news in the news here. It's the order that determines columns. That's all that I can tell you. The definition is this. Must be a minus sign there. All right, and when that operates on the on the space-time tensor, on the space-time vector, it produces, or it can produce, when we do the right operations, the space-time interval. So basically, I've just got the 1, minus 1, 1, minus 1, sorry. 1, minus 1, minus 1, minus 1 produces the signs that I need over there, right? And this thing is called the metric tensor. So we're going to be operating these tensors on other things in order to transform them from frame to frame, physical quantities, from frame to frame, or frame to frame. This kind of transformation, the Lorentz transformation, is also frequently referred to, especially by the particle physicists. I don't know about relativists. As a boost. Yes.
Did you say you were going to come back and define the betas later?
Oh, yeah, I better. Yeah.
Yeah, I was wondering what those were.
So gamma, thank you, is 1 over the square root of 1 minus v squared over c squared. And beta is equal to v over c. Thank you for asking. So, examples of the four vectors that we're going to work with will include the charge current, four vector, and the energy momentum, four vector. But any four vector that transforms from frame to frame with a unit is a four vector. Something that you just make up four numbers, and then physically it turns out that they don't transform that way. That could be a vector of some sort, but it's not a relativistic four vector. We're going to need to perform operations in relativistic space-time. So we need to define derivatives and gradients.
Are those tensors as well?
What?
Are those tensors as well?
No. Who said that? Yeah. So we need the equivalent, some sort of four equivalent of the gradient. We need the four equivalent of the Laplacian. And I don't know what else. That's probably good enough. Oh, we need to figure out, well, we do know how to do dot products and stuff like that. But I will I'll repeat this. In a four vector notation, a derivative in a particular direction. I might write, and I deliberately wrote that with, but I'm going to rewrite it in a minute, with a Roman, Latin, I for the moment, not Greek, right? Just to say that this, with a 1 there, actually it would be, is d by dx, right? And if I want all derivatives in all four coordinates, then I could write a vector, which is the derivative in all four coordinates of a partial of a quantity with respect to each of the coordinates. Now, the first coordinate is ct, so there would be a c that comes out front, okay? Actually, I should just write that up here. My space-time coordinates, x mu, are ct, x, y, c, the Cartesian coordinates. Just give you something to work with here. So I'm taking derivatives with respect to each one of those, and d sub mu is all of them. Sometimes that's written like this, but most of the time like this. Del mu. And writing it out, that's this is 1 over c d by dt, d by dx, d by dy, d by dz. And this is the covariant form. And the contravariant form is 1 over c d by dt minus del. This is del. The three-dimensional del. This one's contravariant. I don't think I need to say too much more. Let me comment, though, that when the del operator operates on a scalar field, phi, for example, that's going to result in a vector, or vector. The other operation, yes.
So the only difference between covariant and contravariant of that is the negative sign out in front?
For the derivatives, yes.
So essentially you still apply the same operations?
Yes. And because this is a vector, we could do dot products, we could do cross products, right? And they're going to be defined in the same way. Yeah.
Aren't cross products when you're dealing with 4D vectors a little annoying because you need 3 vectors for them or something?
Yeah.
Are we
They
going
are.
to work with them in here?
No.
Thank you.
It turns out that whenever we actually need to take a cross product of some sort, there's going to be a 3-dimensional cross product, not a 4-dimensional cross product. Dot products that we're going to take here will frequently be for 4-vector dot products.
But those are relatively easy compared.
Okay, so our first new 4-vector then. We'll call the current 4-vector. And we want to construct something that converts in the same way as the position 4-vector, right? But that includes current, and if it includes current, it should also include charge somehow. So let's see, current 4-vector. What are the things that we might want, that we will need, right? We're going to have the density, the charge density, and we've got to worry about the 3-vector current. Okay? And when charge flows, we have to worry about a actual 3-vector current. We do have 3-dimensional, actually it's a 4-dimensional equation that tells us how things have to be related. And that's called the continuity equation, which basically says that what flows in must flow out. Right? If you like, it's Ampere's law, but Ampere didn't think about it this way. No, not Ampere. Kirchhoff's second law. Divergence of the current plus the rate of change of charge in a volume with respect to time adds up to 0, conservation of charge. So we want to make, yes,
Is that J a current or is that J a current density?
current density. Thank you. Yes. And actually what we're talking about here is a charge density and current density 4-vector. It's called the current 4-vector, but it's current and charge density. Okay, we need to make something that's going to obey this, charge conservation, right? And transform like that under Lorentz transformations. Okay? So we can start with some definitions in a given frame, right? The current density is equal to the charge per charge the density of charges and the velocity. Oh, good. We know that we're going to have to transform something here, and it's a good thing that we see velocity there because we know how to transform that in Lorentz transformations. Okay, and we know that the charge density is charge per individual charge times the number of charges, right? But the charge density, the number density of charges, yes.
Wouldn't it be total charge divided by number of charges?
This
Density?
is,
For looking at density?
this is density.
Mm-hmm.
This is charge per particle times number of particles
Volume.
per unit volume. Yes. Just assume that everything that I say is divided. No, that's not true. Every time I seem to be making a mistake there, ask me, and I will decide whether I need to correct myself or not. Yes, so usually I reserve little letters, small letters, to mean densities, right? So current density, oh, that's not. That's charge per electron. Electron density, velocity. This is actually drift velocity because it's the sum over all charges in the system. Right? In some frame, or actually in any frame, the charge density is gamma times the charge density in the proper frame of the charges, the average, the one that's moving along with the average drift velocity. So then I can rewrite the current density, Q gamma N0 V. So I transformed the charge density, the number density of charge, and here I've got Q gamma N0. So then we can ask, so we see how things transform, right? The equivalent 4-vector thing that's going to actually transform has got to include velocity and charge density. And the 4-vector, J, is going to be equal to Qn0 times gamma c for motion along the x direction, gamma Vx, Vy, Vz. So that thing is does transform in the same way as the position. So I'll write that one over here. Current 4-vector is gamma c, gamma Vx, y, z. For transformations along the gammas appear there, for transformations for motion along the x direction. Yeah. Oh, I dropped them. Thank you. And the continuity equation now reads like this. We're going to find out that Maxwell's equations take a similarly compact form when we get to that. So that's one 4-vector. All right, let's take a short break, and then we'll continue with the potential 4-vector energy.